Hi, I'm Takayuki Murooka from OMRON SINICX Corporation. Today, I'd like to talk about EXINet, explicitly implicitly conditioned network for multiple environment symmetrical transfer. Symmetrical transfer is one effective method to reduce the cost of collecting data with real robots, and various kinds of methods have been proposed to reinforce the symmetrical transfer, such as domain randomization or domain adaptation. However, previous works of the symmetrical transfer dealt with a few dynamics conditions, resulting in the less applicability to the real world. In this study, we explore the symmetrical transfer in multiple environments, including a wide range of dynamics. To verify our method, we apply it to the pushing object task, where pushed objects have various dynamics. Here, I'll introduce the structure of our proposed method, EXINet. Our key idea is to condition the network with two classes of dynamics parameters to deal with the multiple environments. One is explicit dynamics parameters, which is easy to quantify the physical parameters such as mass, COZ position, friction coefficient, etc. The other is implicit dynamic parameters, which is difficult to quantify the physical parameters such as object shape, material, etc. Then we build the predictive model, whose input is the current state and action, and whose output is the next stage, represented as a deep neural network. We embed explicit and implicit dynamics parameters to this predictive model, and this extended predictive model is EXINet. In order to train EXINet, first we generate the dataset of the current state and action at the next stage by changing dynamics parameters widely in simulation. For the pushing object task, we change object mass, COZ position, friction coefficient, and shape. Those dynamics parameters, except for object shape, are defined as the explicit dynamics parameters since we can easily quantify them. Only the object shape is defined as the implicit dynamic parameters since we don't have any good idea to quantify them. With this dataset, we train the weight of EXINet and implicit dynamics parameters as parametric biases. Note that while training, the explicit dynamics parameters are given as a part of the dataset. Parametric biases are one of unsupervised learning methods to embed a certain data to the latent space only with their label. Now, EXINet represents the predictive model in conjunction with a wide range of dynamics information. Next, I'll explain how EXINet can be applied to manipulation in the unknown environment. We estimate the current dynamics parameters and calculate the action with the estimated dynamics parameters in real time. To estimate the current dynamics parameters, we observe and collect the dataset in the current environment while manipulation, and with the loss function of the predicted and observed state, we optimize the expressed and implicit dynamics parameters iteratively using the backpropagation of EXINet. To calculate the action with the loss function of the predicted and goal state, we optimize the action iteratively the same way as dynamics estimation using the backpropagation. This action calculation method is known as deep model predictive control. Finally, we show the results of pushing objects in the real world. As shown in the video, the robot successfully pushed a variety of objects to the target poses. Moreover, our method showed a higher success rate than the recurrent structures network mainly used in the previous works for the symmetrical transfer. Thank you for your watching. More detail about comparative experiments and their discussions are written in the paper, so you can check it out if you like our paper.